Making liquid oxygen is pretty straightforward if you happen to have some liquid nitrogen, which I do. So what I've got here, my cylinder of oxygen, and I'm passing the oxygen through this copper coil here, which is immersed in liquid nitrogen. The oxygen has a higher boiling point than the nitrogen, so it condenses in the coil, and so by the time it comes out the other end of the tube, it's a liquid. So this has been going a while. I've nearly got a full tube, so I'm just going to. Whoa! Yep, that's pretty full. So I'll just put this down over here. Okay, yeah, so good. Half litre of liquid oxygen here. I'll just show you what it looks like. So there you go, that's liquid oxygen. The first thing you'll notice about it, I would think, is that it's actually blue, which is a bit of a surprise. Colour quite often is just a manifestation of the way that light interacts with the electrons in materials. So straight away, this is saying that there might be something a bit funny about the way the electrons are arranged in oxygen molecules. What that is actually is that there are unpaired electrons. Electrons usually like to pair up. But in oxygen, there are a couple that doesn't happen to, and we call them unpaired electrons. And there's actually another unusual property of oxygen that arises from the unpaired electrons, which I want to show you now. Right, I've got a great big magnet here, as you can see, just a couple of nuts between the poles, just to bring the poles slightly closer together. And I'm going to pour the liquid oxygen between the poles, like so. And there you go, you can see the oxygen, until it boils away, is sticking briefly between the poles of the magnet. So what's going on here, again, is because of those unpaired electrons. Electrons, any electron in an atom or in a molecule contributes a small magnetic dipole moment. Normally when those electrons are paired up, the magnetic dipole moments cancel out, but obviously with oxygen, you have these unpaired electrons, that doesn't happen. So as a result, the whole molecule has a residual dipole and acts as a tiny little magnet. So I'll keep on pouring this in and we can keep on looking at it. Now normally when the oxygen is just sitting in the flask or in the air, all those tiny little magnets are pointing in random directions basically, so they all cancel out, so there's no net macroscopic magnetic field. But when you introduce the permanent magnet to the oxygen here, then you get those magnetic molecules all slightly aligning a bit more than they would normally, and that creates a net magnetic field. So the induced magnetic field then interacts with the magnetic field from the dirty great magnet, and you get the oxygen sticking in the poles. Now this phenomenon is something called paramagnetism, where you get an induced attractive magnetic field in a material. And I think it was actually Michael Faraday who discovered that oxygen was paramagnetic right here at the RI. So one final thing, seeing as this is liquid oxygen and this is the Royal Institution, I'm going to set something on fire. This is the classic demonstration of oxygen relighting a glowing splint. Lovely.